We finally prove the proposition, which is the only piece left. Before going to the proof from very close and with all the details, let's just skim through the proof. So the proof will be the following. We want to find this. Again, what's the proposition? We have some nilpotent operator Tn, and we want to find a sequence of vectors that if you take n, and again, eventually it goes to 0, and then another one that eventually goes to 0, and another one that eventually goes to 0, and so that when you take all these vectors here together, they form a basis. If this is the case, then the matrix of the operator n with respect to that basis will be a Jordan basis, a very nice Jordan basis. So this is what we are looking for. So the challenge is to get enough many vectors that form a basis. We need this thread here to be very long. How can we get this thread here to be very long? Well, we need to search for vectors that are in the range of n to the k for k as large as possible. Otherwise, we won't find as many. Okay, so this is the trick. And if we just pick a vector at random, typically that vector will not be in the range n to the k. So here's the proof. It's a construction, and we do as follows. We'll define uk to be the range of n to the k. So we know that if we take un, that's the range of n to the n, but n of the n to the n is the 0 operator because n is nilpotent, so it only has 0. So range n to the k, as you increase n, this space is shrinking. It's getting smaller and smaller. Okay? And we're going to do the following. We're going to start by picking a basis to this vector, to this space. What's the basis? The basis for this zero-dimensional vector space is just the empty set. The empty set is linearly independent and it spans this. It's a kind of weird, but that's the right way to look at it. So the empty set is a Jordan basis because, well, the matrix of an operator on this space is just kind of the empty 0 by 0 matrix, and that's a Jordan matrix somehow. And what we're going to do is now we start from n and we just goes lower and lower. Now we go from n to n minus 1 to n minus 2. We're going down, and at each point we're adding. This space is increasing because we are decreasing k here. So we're adding more elements to this basis, and we add more and more and more in a consistent way, in a very careful way, so that in the end we'll get B0. B0 is a basis for U0. What's U0? The range of n to the 0. N to the 0 is the identity, so this is simply the whole vector space, G. G, if you think you are inside the proof of the existence of Jordan basis for any operator, or V, if your world is V and the only thing that exists in your world is this operator n. So let's call it V for us. So U0 equals V. And okay, I did the first part of the proof already, so let me just skim through the rest before we actually go into the details. We're going to find more vectors by solving an equation. So we have some vectors which are at the tip of the thread, so they are mapped to 0, and we're adding more vectors before them, and adding more vectors before them. So we add more vectors by solving equations, and we show then that the vectors we add still keep the property that the whole collection is linearly independent. And then we're going to prove that it's still linearly independent. Once we have proved that, we're going to we need to add a few more vectors to get a basis for UK. So we just extend the basis we currently have. The problem is we want to construct a Jordan basis. And so we need to fix the vectors that we find. We need to tweak them and subtract something from them so that they don't destroy the property. What's the property? The property is that we have a collection of vectors, then n apply to that vector, then n apply to the next vector, and so on. So that's the property we don't want to break. So if we just add another vector here, and it's not clear that this vector, when we take n of this vector, it goes to 0. And if it doesn't go to 0, it goes to another vector, and maybe that vector will ruin the property that this collection is linearly independent. So we need to fix those vectors. That's what we're going to do. And once we got that done, then we will have shown how to go from n, from k to k minus 1. Okay? So we start from a Jordan basis for bk plus 1, and then we find a Jordan basis for n restricted to uk. That's how we're going to do it, and the picture in the end that we get is this. So we take this number k here is not the dimension necessarily, it's just the last number before you start before the range becomes 0. So you find linearly independent vectors. In this case, they will be eigenvectors that go to 0. Then you find vectors that are mapped to those vectors, but maybe this doesn't quite span the space here. What's this space here? uk minus 2. And then maybe we have to add one more, but we make sure we add one more that goes to 0. And we keep doing this. So this is what a Jordan basis looks like. It's a bunch of vectors organized as threads. All these threads, they end at 0. And all these vectors, they are linearly independent. So this ensures that the operator expressed with respect to this basis will have a Jordan form. You can take this as the very definition of a Jordan basis.